the Lord, seeking clarity and purpose for today's session. Dear Lord, we are humbly asked for your guidance as we embark on this journey of learning. Bless us with the wisdom to understand complex ideas, patience to approach challenges, and openness to embrace the new perspectives. May this time together be enriching, bringing us closer to knowledge that can serve others and benefit to our world. It is a privilege to welcome each one of you to the 7 days online FDP program on quantum computing. As we gather virtually, we are here to explore on one of the most groundbreaking fields of modern science, quantum computing. Before we officially kick off, I would like to extend my welcome and the heartfelt thanks to all who have generously supported for this event. Firstly, I would like to extend a warm welcome to the distinguished keynote speakers for this event. We are truly privileged to have the experts who have made significant contributions to the field of quantum computing and beyond. Their knowledge and the insights will guide us throughout the duration of this program, helping us deepen our understanding of quantum computing and its practical applications. I extend my gracious welcome to our Vice Principal, Sir, Dr. S.N. Suresh, Sir, who has supports us in organizing this event. Your unwavering support, dedication, and hard work have been instrumental in bringing us this event and remarkable one. On the same note, I would like to extend my heartfelt welcome to our respected head of the department, Dr. S. Raja, Sir, who has been guiding force behind this program, bringing his vision, dedication, and unwavering support to ensure the success of this event. I welcome Mrs. D. Uma Maheshwari Ma'am, Head and Assistant Professor, Department of Physics for this event. Her involvement in the organization of this program reflects her commitment to promoting interdisciplinary learning and fostering collaboration between departments. Last but not least, I welcome all the participants and the faculty members from the various colleges and our college who has joined us with us today for this event. With this note, it's my honor and privilege to invite Dr. S.N. Suresh, Sir, to deliver the felicitation address for this event.
Audible? Am I audible, man?
Yes, sir. Yes, sir. Yes, sir. You are audible.
Very good morning to all the dignitaries, the participants from outside Rathinam and inside Rathinam, the head of the departments and faculty members. I wholeheartedly congratulate the Department of Computer Science and Department of Physics, both head of the departments and faculty members for organizing this wonderful event, quantum computing, the need for an hour, and I hope this program will be a platform where the students will expose to latest development and current trends in the area of quantum computing. I would like also to mention this program is organized under the sponsorship of DBT Star College scheme. I thank the management and the DBT for giving an opportunity to conduct this program under the DBT Star College scheme. I appreciate the efforts taken by Dr. Raja and Uma Maheshwari ma'am in organizing this event. I hope this event will be eye-opener for the students what is really happening in the area of quantum computing. Once again, I congratulate and thank both the departments for organizing this event. And also, I would like to thank all the resource persons who have given their consent to serve as resource persons. Once again, I thank you all, and I wish this event to be a great success. Thank you. Thank you so much.
Thank you, sir. Thank you so much, sir. Before we move on to the session, here is a brief intro of the today's guest, Professor Suhadip Mitra. It's with a great pleasure I introduce Professor Suhadip Mitra, an esteemed academician and researcher who is currently serving as an associate professor at the International Institute of Information Technology, Hyderabad. He has a distinguished academic background, having earned PhD in theoretical physics from the Indian Institute of Technology, Kanpur in 2008. He also holds an MSc Physics from IIT Kanpur and BSc in Physics from DA College, University of Calcutta. The professor has held several prestigious academic roles throughout his career. Prior to his current position, he has served as an assistant professor of International Institute of Information Technology, Hyderabad from 2015 to 2022, and briefly at Tech India in the University of Kolkata in 2015. He has also held an important research positions, including senior project scientist at IIT Kanpur and CNRS postdoctoral fellow at Laboratoire de Physique, France. His research contributions are significant and diverse with the key publications exploring advanced topics such as Higgs bonds in 5D theories, dark matter candidates, and vector-like quarks. He has made substantial contribution to understanding cosmological symmetry breaking and dark energy, significantly enriching the fields of high energy physics and cosmology. As an educator, Professor Suhadip Mitra has taught a wide range of courses, including quantum mechanics, particle physics, thermodynamics, and electrodynamics. He has also introduced advanced courses like machine learning for particle physics and integrating interdisciplinary approaches to solve the complex problems in physics and computer science. He has also actively involved in academic governance, serving as an several important committee members, including Gender Grievance Cell and the Academic Cooperation Committee. Beyond his academic and research duties, he is dedicated to the student life, having served as a coordinator and vice chairperson of the Cultural Committee at International Institute of Information Technology, Hyderabad. We are truly honored to have such an esteemed speaker today. His wide ranging contributions to both theoretical physics and education, along with his leadership in fostering a vibrant academic, making him an inspiring presence to his event. We look forward to his invaluable insights and discussions that we will follow. Over the session to the speaker.
Hello, am I audible?
Yes, sir, you are audible.
Yeah. Thanks. Oh, thank you for the very generous introduction. You might be wondering what a particle physicist is doing with quantum computation, but I hope I'll be able to convince you that I am actually not that far off from the field after all. Okay, so just let me see if I can share it. This is enabled now. Are you able to see the screen?
Yes, sir, we can see.
Okay. So I'll do one thing. I'll turn off my video, okay? Because that unnecessary clogs the net.
Yeah, okay.
But whenever somebody asks question or if you want to see me, then I can turn it on. No problem. Okay.
Okay, okay.
And also, I cannot see the screen. So if somebody is raising hand, I will not be able to see. So I request one of you to please make a note of the questions, and I can stop in between. I have no problem. So just some of you moderate it. That will be helpful.
Yeah, okay, sir. I will notify you, sir.
Okay. So once again, let me thank you. I'm truly honored that you have asked me to give this lecture. I'll try to introduce you to quantum computation. I'll try to tell you what is this about. You all are familiar with classical computation. That means the regular computer and whatever computing task you do regularly with your mobile phone or computers, laptops. Quantum computing is a slightly different thing, or it is at a different stage as of now, and my challenge is to convince you of that. Okay, so in different in various ways, and I'll try to show you how this is different. Okay. However, before I begin, I want to start with some minor disclaimers. First, okay, this is an academic talk, so I have used images from the web freely. Okay, so I have not, although I have actually credited the sources as much as possible, I am not sure that I have not violated any copyrighted thing or anything. Okay, so before you share this, if you want to share this on platforms like YouTube, you have to be careful about that. So that's my disclaimer that this is purely for academic purpose. Okay, and second thing is that uh, quantum computing, it's actually hard. Hard means, for example, look at this. One of the pioneers of quantum computing, Scott Aronson, who has written many books, many papers, and he's one of the giant of quantum computing. He wrote an article, and the title says that what makes quantum computing so hard to explain. Okay, so this is my second disclaimer. So unlike many other fields, quantum computing is actually in true sense multidisciplinary field, because it's born out of physics, as you will see, and a good amount of computing ideas goes into it. But it's not just physics and computing ideas. There are good amount of math and, of course, common sense that is required. Okay, so unfortunately, because of the quantum nature of the world, or quantum nature, it's not possible to explain every ideas without mathematical symbol and stuff. So that itself makes thing slightly challenging for many people. Okay, I'll try to make it as simple as possible, and you are welcome to stop me if something is not clear. You are welcome to interrupt me. I'll take all these questions, but it's not possible to explain everything in very simple terms. You need to know a little. So what I will assume that you are all familiar with basic level of quantum mechanics. So by that I mean that you have heard about quantum mechanics. You know at least a little bit of what does this mean. Okay, I don't assume any mastery of quantum mechanics or any science for that matter, and I'll try to walk you through the field as I go. Okay, so with this disclaimer, let me begin. So near the end of September, early October in 2019, we all woke up suddenly to the news that Google claimed something called a quantum supremacy. Okay, so it was all in the newspaper suddenly, and Google came up with a paper which is very well known and well cited now in Nature, that says that quantum supremacy using a programmable superconducting processor. I'll explain what that means. So quantum supremacy is okay, I'll explain the word as I go. So what Google made is, so they claim that they have made a quantum chip. Okay, just like our normal desktop or laptop computers or even servers have processors. So they have made a quantum processor which can do quantum computing tasks. Okay, and not only that, it is big enough and accurate enough to do or perform some calculations which they claim that cannot be done on a classical computer in a reasonable amount of time. Okay, so this is the essence of the word quantum supremacy. So something that quantum computers can do because they have some special powers that we will see, at least that is the hope, that normal classical computers could not achieve. Okay, so this is the picture of their processor. So on the right, you see a big tube-like shape that is actually the cryostat, because it's built on superconducting qubits. I'll come to what does it mean by what do I mean by qubit? It is just quantum bit. Okay, so that's called qubit. Uh, so these qubits are inside this Sycamore processor. You see the image on the left. Do you see my cursor? Is my cursor visible?
Yes, sir. It's visible.
Okay, okay. So then on the left, you see the Sycamore processor, and it's essentially just aluminum strips. Okay, so it has 53 qubits corresponding to a computational state of dimension 2 to the power 53. So of the order of 10 to the power 16. Okay, so it's a huge computational space. Okay, and it can compute. Okay, it's and that's why they claim that it's I mean they claim the supremacy over the classical computers. So just to give you the idea what is happening, what is this actually about. So inside this chip, so there are, it is essentially a Cooper pair box. Okay, so superconducting, small minor superconductors, tiny superconductors. The Cooper pairs are trapped inside a square box. You see in the diagram on the left. Okay, so in that square box, whenever you trap them, so their energy level splits. Okay, and that is how you can map it to qubit. Okay, so this quantum energy level that you might have seen when you have solved the one-dimensional particle in a box problem in quantum mechanics. Okay, so it is, if you understand that, then you will understand that when, so this is essentially a map to that problem. So individually, all these processors are a trapped superconductor, so conducting Cooper pair inside a box. Now, with this, I mean, why this claim was important? Because the main question that these guys were trying to address is that can a quantum system be engineered to perform a computation in a large enough computation, in this case Hilbert space, and with a low enough error rate to provide a quantum speed up. So the first challenge, quantum computers, it was possible to build from long enough. Okay, people could build quantum beats, and with that they could do perform small calculation from quite a bit of time. But the challenge was scaling it up, because you see, unlike quantum classical computers, adding extra bit is not very simple. Not actually not simple at all. Not it could be a complete technology overhaul. Okay, because the computing power goes up with exponentially. And the second thing is that, okay, you can build a good enough quantum computer, but can you find a problem which is where you can actually show the supremacy? For example, you have to find a problem that you can solve in that computer, which you cannot solve in classical computer in similar time or in a reasonable time. Then only you can claim supremacy. So if you can do something that you can easily do on a classical computer, then the quantum computer is not that useful, right? Because it requires a huge cryogenic system and it is a big box, whereas classical computers are, I mean, most of the time they're just mobile devices, and we are so used to them. So there is not much case there for the quantum computers, right? But what Google claimed, that they have showed that they have done something which you cannot do in classical computers. So that was the main reason for this big hullabaloo. Okay, so they compared with the Sputnik movement. So the guy who actually announced this to in front of the reporters and all. So he came out in a space like spacesuit like jacket and all that. And Sundar Pichai linked the movement to this, like the Wright brothers' first flight or the first rocket to escape Earth gravity and so on. Okay, so it was of course a big, very big news event at that time, 2019, end of 2019. So the word quantum supremacy was coined by John Preskill, who is another giant in this field. He has been kind of developing this field, or holding this field for long. Okay, he is one of very well known researcher. Okay, so I mean, then he actually explained, wrote an article. It's just after the Google news. Okay, so he explained why he called this quantum supremacy. So I'm quoting some important lines from the article, and this article is freely available in Quantum Magazine. You can read it. So the catch, as the Google team acknowledges, is that the problem their machine solved with astounding speed was carefully chosen just for the purpose of demonstrating the quantum computer superiority. So Preskill is actually coming out and looking at the Google's result, Google's claim that they have shown quantum supremacy over the classical computers. And he's saying, look, the Google team has actually done something, but the problem is essentially of no practical use. It's a tailor-made problem just to show that something is better than other. But that this doesn't mean that the quantum computers are now will take over the classical computers and suddenly we are in a quantum era. He's saying that that's not the case. Okay. So in brief, the quantum computer executed a randomly chosen sequence of instructions, and then all the qubits were measured to produce an output bit string. So this is what they did actually. This quantum computation has very little structure, which makes it harder for the classical computer to keep up, but also means that the answer is not very informative. And this is what I was saying, that the problem is chosen just to show quantum supremacy, nothing else. However, the demonstration is still significant. By checking that the output of the quantum computer agrees with the output of a classical supercomputer, in case where it doesn't take thousands of years, the team has verified that they understand their device and that it performs as it should. Because these are the people who have been arguing, and we will go back to the history a little, and we'll see how it's all started, who have been arguing that quantum computers are something special. They can give us immense powers over classical computers. Okay, so that is the source of this quantum supremacy. So Google has verified a problem, which is, even though it has very little practical value, but it is still important because it has shown that at least the hypothetical power that a quantum computer can offer may not be hypothetical at all. It might be actually physical. Okay. So right now, we could say that we are not in the quantum computing era, but we are in the NISQ era, which a term which again Preskill coined. It's the noisy intermediate scale quantum computing era or quantum era. Okay, and we will see that what is this about in a while. So this is actually the problem that the schematic of the problem Google solved. Okay, so these are some random really chosen registers, and they are picking up numbers randomly and performing a task. But it is purely random, which it can do much faster than classical computers, classical supercomputers. Of course, if Google proposes it, then IBM disagrees, and so IBM came up with a counterattack, and they said that look, whatever Google is claiming, they are correct on the quantum part, but the claim that they have shown supremacy over the classical computers, that's wrong. Why? Because they said that they are claiming that something that cannot be done in classical computers in a reasonable time, that part is wrong. And IBM showed, or again counterclaimed that. So I can quote from their paper, IBM's paper. In the paper, that means the Google paper, it's argued that their device reached quantum supremacy and that a state-of-art supercomputer would require approximately 10,000 years to perform the equivalent task. We argue that an ideal simulation of the same task can be performed on a classical system in a 2.5 days and with far greater fidelity. This is in fact a conservative worst case estimate, and we expect with additional refinements, the classical cost of the simulation can be further reduced. Okay, so now, so what it points to is that there could be some problem, or now more or less everybody agrees that the supremacy claim was probably an hype. Okay. However, what Google showed that they can build a big quantum computer and with that they can perform meaningful tasks. Okay, so of course in that particular paper they chose something uh, which is not meaningful, just to show what they thought as a demonstration of quantum supremacy. But after that, they have opened it up for academic research, the quantum chip, Sycamore chip, and they actually solved quite a good amount of uh, problems which can have meaningful implications on science directly. For example, soon after that, so this is I mean, it's a two-dimensional Hubbard model. Okay, so this paper talks about, this is older paper, 2015. Okay, so they talk this Hubbard model is an approximate model, so that describes those who work on material science and quantum chemistry. They will know very well that this they talk about. I mean, this model actually describes this conducting and insulating phases. Okay? So essentially, it's a simple model of interacting particle in a lattice. So you have a kinetic term that allows for hopping between lattice sites, and then there is a potential term that describes the on-site interaction. Okay, so it's a very well-known model, and this paper came up with some solution. This has nothing to do with quantum computing. What Google did is actually they reproduced their calculation using the quantum computer, and they found that their results are matching with the classical simulation of quantum task, because this is actually a quantum science. I mean, whatever they're describing is quantum science, and they were doing, in this paper they did it with classical computers using simulators, and the results were matching with Google's result. Okay. So they verified that using Sycamore chip, they can describe the property of quantum ring. So quantum ring like this. So this is something really remarkable, because the classical simulation of this is very complicated and takes huge time and compute cost and everything, whereas a quantum computer can do it very fast and much faster than the classical thing, and their precision is good enough. That means the error rates and uh, are manageable, at least in this case. Okay, so this is the first demonstration of some meaningful calculation, meaningful in the sense that can have impact in the real world. Okay, and then all they did, they mimic the Hertford on a I mean, they use this. They opened up this chip for academic calculations, and people used it for a lot of calculations. For example, here I show one article which is doing Hertford on this superconducting qubit quantum computer, which is the Sycamore actually. Okay, so this is the simulation they performed, and again it made to newspapers that the Google has achieved a quantum chemistry milestones. Okay, so this is essentially this. They simulated first a 12 hydrogen atoms chain, and then they simulated using quantum computer that how hydrogen and nitrogen atoms interact. So again, if you know about quantum chemistry, you will know about Hartree-Fock approximation. So those who have some prior exposure will appreciate the deep challenge that lies in that domain. Not only that, they realize something fantastic. So topologically ordered state, this is something. So we know that in three dimension, three space dimension, that is, we have spin half particles, fermions, or spin. Uh, I mean, fermions and bosons. So integral spins and half integral spins. Okay, uh, these are the two possibilities. But if you go down to, if you make the dimension, the space dimension, not three but two. Okay, so then you have another possibility, and so that's neither like fermions nor like bosons. So their statistics is different. So essentially, it's this that whenever you interchange, you pick up a complete minus sign or a plus sign, depending on whether you are dealing with a fermion or a boson, okay, in 3 dimension. But in 2 dimension, it turns out that you can just you can introduce a relative phase, okay, and so it's neither like boson or not like fermion, so they are called anyons, okay, and these with these anyons you can have different phases, okay, quantum phases, and so far it was completely I mean just hypothetical calculation, because this showing this, demonstrating this takes really big computing capability. But the Google guys with academic people, they collaborated and demonstrated with the quantum computer, that Sycamore, that you can actually achieve this. So this is quantum uh, or topologically ordered states. And another thing, so I'm just showing you some random news that came out after their announcement on 2019, and so for next 2-3 years they supported a lot of academic research. They still do. So something very interesting came out, and even recently, as in I think few months back, it was on the news, because what they claimed is that they have they have shown the existence of something called a time crystal. So we all know know about crystals, right? Crystals means that inside there are repeating structures. So there's a periodic structure that repeats as you go across space. Okay? So the time crystals are interesting because this repetition happens in time and not in space. So if you wait over time, so it's like the time resets inside the time crystal. Okay? So Franz Wilczek, who won the Nobel Prize for discovery and QCD, which forms the standard model of particle physics. He is a very well-known particle physicist. So he actually conceived this idea in 2012. He said that, look, if you can think about crystals, then you can also, we should be able to think about crystals in time. Okay, so that means something that repeats. So it's like going back to the time again. It's just like the Matrix movie, if you have seen it. So somebody goes on left side and they emerge again on the right side after some time, and this goes on, keeps on happening. So it's like a trap of time. And I quote this news because there is a slight India connection. So Vedika Khemani, she is a condensed matter physicist at Stanford. So this was her demonstration, kind of, because she is the one with her two or three co-authors, I think, three co-authors. So when she was a graduate student in 2015, this is how she actually took this idea to show that this is a possibility. Okay, and of course with quantum processor now they have shown it. So this paper is, I have taken the snapshot from archive, but this is of course now a published paper, and there are more follow-ups. Okay, you can easily go to Wikipedia and just type quantum time crystals, or just time crystals. You will see a lot of references there. So I'll not show any more news, because I think I have established the hype, or what the hype was about. Why suddenly people started talking about quantum computers, or outside the academia. Of course, academia was talking about quantum computers from quite some time. In fact, it is from Feynman. But now even the governments and the companies have taken this very seriously, and people means especially the governments are doing a huge amount of investment in this to build quantum computers and quantum, what they call quantum communications and quantum internet and so on. Okay? So suddenly it seems that we are in the quantum era. Okay, and let's see where we are as we go, and we'll see. So if you think about it, everything started from this man, Feynman. Okay, so on the top of my slide, I have given the link of, reference of the paper. You can go and read it. It's very simple and it's brilliant to read because it's written by Feynman. So he can probably the best person to explain a new idea, right? So he says in that paper, uh, so he actually proposed in the previous year, okay, he said that, okay, if you want to learn about nature, so why not build a computer that utilizes the power of nature? So essentially what he was saying, that why not learn about nature with nature itself? Okay, so this is in 1980s, okay, early 80s, 81. And at that time, computers were very slow. Their capacity was, in today's world, it will be like frustrating. I mean, it's unbelievably basic. But at that time, you could think of, okay, the classical computers might be limited. We may not have the technology to do this, but in principle, one can think that we can use nature's tool to simulate nature, okay? To simulate nature or understand nature, right? So what better tool can there be beyond nature? So he proposed that, can we use the best tool available to learn about nature? I mean, each atom is just a point. So I'm quoting because this is brilliant and with clarity, okay? I mean, each atom is just a point which has numbers associated with it, with quantum mechanical rules. So these numbers are nothing but the quantum numbers. So like spin, charge, and also mass and so on. For example, the spin waves in a spin lattice imitating Bose particles in the field theory. I therefore believe it's true that with a suitable class of quantum machines, you could imitate any quantum system, including the physical world. But I don't know whether the general theory of this intersimulation of quantum system has ever been worked out. And so I present that as another interesting problem to work out the classes of different kinds of quantum mechanical system, which are really intersimulable, which are equivalent, as has been done in the case of classical computers. So he was essentially saying that, okay, so let's figure out the complexity classes, okay? Just like we do in the for classical computation. Let's see that what kind of complex problem we can solve, what kind of problems are in principle possible, because this is 1981. This is just essentially one man's idea at that time. Can you do it with a new kind of computer, a quantum computer? Now it turns out, as far as I can tell, that you can simulate this with a quantum system with quantum computer elements. Okay. And then in this paper, and I think he wrote another paper on this. Uh, and by the way, now his lectures on quantum computing are now available as a book. I think it's lectures on quantum computing. It's brilliant to read. Okay, anybody with a high school level of mathematics can understand it. And it's brilliant in clarity, and you can get that what this man was trying to say. And in a lot of sense, we are not there yet, okay, but we are walking along that line. So you can see the dream that drives everything, of course. So this is the answer. So the question that he asked in the last, that can you do it with a new computer, kind of computer, a quantum computer? So this is, in a sense, the answer to that question. Okay, so Sycamore, of course, this is, I'm not saying this is the only answer, because there are other quantum computers and good simulators available. But this is probably the strongest candidate or the best one that there is. Okay. So if there is any question, anyone, I can't see. No? Okay. So, yeah. Yes. Yes, I
Morning, sir. This is Dr. Srinivasan.
hello. Yeah.
Can you hear me, sir?
Yes, I can hear you.
Yeah, that was nice presentation, sir. I have just a query on what you have just presented right now.
Mhm.
Regarding the construction of this quantum computing and chipsets, as you have the Syncamore and all, what is
Sycamore,
the
yeah.
stipulated time that would be required to construct a single machine that could deliver an appropriate output as required by the user?
Oh, this. So you. So the thing is,
Yes, sir.
building this is a. I mean, Google will not disclose this technology, right? So if you want
Yes.
to build it from scratch, so I think we can probably build 2, 4, 5 qubit quantum computers within reasonable time with the
Okay.
technological know-how, as far as I'm aware, okay, today in
Mm.
India. But going beyond will
Okay,
take
sir.
time, and so I mean, it's not easy to say actually. So
Okay.
because the reason is when we reach there around 50 qubit, Google will probably far ahead than us. So it's I'm assuming you are asking about
Yes.
in our context, Indian context.
Yes, sir. Yes, sir.
So any other
Hello.
question? So because I'll start on a slightly more technical aspect of this presentation then.
Sure, sir. Sure.
Participant, if
Yeah.
you have any questions, please raise. You will unmute.
Sorry, can you be louder, please? I can't get you.
Dear participants, if you have any questions, please raise. I will unmute your mic.
I can't actually hear.
Submit questions.
Okay, sorry. Okay, I can take questions even later, no problem. So
Oh,
you can ask me in the second break or third break or at the end, no problem. Okay. So let's see what is this qubit. Okay, so how do we understand qubit? We all know about classical bit, right? It's like a binary system, 0 and 1, but you can also map it with voltage, which is generally the case in our computers. So say 0 is low voltage and 1 is high voltage, something like that. Two-step system. It's a binary system. So this is classical bit. Okay. And on this, everything runs. Everything, that means the phone you are holding in your hand to the computer you use regularly at home or your workplace. This is what it is. Okay. You can of course do computing with non-electronic stuff as well, but everything is based on this classical bit. Okay, so it's a binary mapping. But quantum bit is a different. Okay, so you can we will see what this quantum bit is. I mean, physically is about. Just like I told you that okay, Google's Sycamore is actually a superconductor conducting Cooper pair that is trapped inside a box, three-dimensional box. So to think about quantum bits, it's like this. You can say that okay, there is a zero state and a one state, but a qubit is a linear superposition of all. Uh, I mean, these two sets. It's an arbitrary superposition of these two sets. I'll explain what do I mean by that. But before that, let me just quickly explain or explain what is this notation about. Okay, so what I'm using is called Dirac's bracket notation. So this 0 and 1 are the the quantum 0 state and quantum 1 state. So if you think of an electron, 0 state could be like okay, the spin down state of an electron, and 1 state could be spin up state of the electron. Okay, So what this line is saying, that an arbitrary electron, if you don't know what is the spin of that electron, that means the orientation of the spin, then that the spin of the electron is like a superposition. So the electrons simultaneously exist on the up spin state and down spin state, and it is not just up and down spins, it's all possible linear combination. So it's like because alpha and beta are just arbitrary complex numbers, okay. uh, and it's a infinitely possible superposition of this zero state and down state. So this means an electron, until you measure the spin of the electron, it's a all possible combination of up spin and down spin, okay. But it is in a superposition state, which I'll explain shortly, okay. So these quantum states are, so they live in a space called Hilbert space, which the mathematicians call as L2 space. So where the um, uh, 2 norm is or is actually well defined. It's square integrable. But anyway, if you don't know the mathematics, that's also fine. So for us, it's like this. If you think this Q's, the states, this quantum bit, the Q bit Q as state, so which is like a vector, then the square of the length of the vector is calculated in the second line. Okay, so you see a bracket and a bracket which, so this is called a ket. Okay, so the first one Q here, it's called a ket, and you see in the next line when I say write normalized, so this side the bracket is on the other side. Okay, it's called a bra. So bra and ket creates this bracket notation. Okay, so this is like calculating the square of the length of a vector, which is 1. So you know in quantum mechanics that uh, the quantum states, for example, if you have, if you have seen Schrodinger equation, the psi, the state function, the wave function that you solve, you have to take the mod square of that function to calculate the probability of finding that particle in some location. Okay, so this Q is essentially a notation for that psi. Okay, so this is in short a smarter way of writing things, and this notation is actually immensely powerful. That's why it's standard. Okay? So all we need to understand that whenever we say normalize, that means we say that, oh, the probability is 1. That means if you measure, so suppose this 0 and 1 are just spin up and down. So then the next line says just that, okay, if you measure the spin of electron, you will find that the probability of finding it up state and down state, if you add these two, which is given by alpha square and beta square, if you add these two, you'll get 1. So probability is conserved. Okay, no problem. So, as I was saying, so this, if you assume that Q is from a vector space, so then this Q, the bra side Q is set from a dual space. Okay, so this is more mathematics, but it's, you can, if you have difficulty in understanding this, then there is a beautiful way to understand this geometrically. Okay, and you don't need a lot of notation for that. What you could do is like you can, so this is, sorry, uh, you can look at this sphere. Okay, sphere on the left side. Okay, this is called a block sphere. So this 0 state and 1 state, you map it to the extreme polar region. So north pole is 0 state set, and you map the south pole as the 1 state. And what essentially we are saying, the electron, the spin of the electron before you measure, it could be anywhere on this surface of the sphere, and this sphere is called block sphere because he was the person who came up with this idea. So, for example, you see the line, the vector called V, which is making an angle theta from the Z direction and a phi from this X direction. So, the theta is the zenith angle and phi is the polar angle. So, if you know the polar coordinate system, then you already are familiar with this system. So, this V could be the state of an arbitrary electron. So that means so classically, if you think this as classical bit, then 0 and 1 were the only two possibilities. So it is either 0 or 1. But in quantum mechanics, you have infinite number of possibilities because every point on the sphere is a combination of 0 and 1, which you can project. So for example, this V is partially, so alpha, so then alpha is cos theta by 2 and beta is e to the power I phi sin theta by 2. So that means so alpha part 0 and beta part 1. Okay, so this is how you can parameterize. So you can just move this point V around and you can understand all these spaces. Okay, so these are different basis choice. So instead of just 0 and 1, you can also work with this plus minus basis. So plus minus basis is just it's a linear projection. So it's I have shown it. Okay, it's the plus combination between 0 and 1 and negative combination between 0 and 1. But these are different basis choice because to describe a vector space you can use the basis is free. It's up to you. Whatever you take is fine. So these are different basis choice that you can do. And this row on the right is called a density matrix. So that tells that that's a way of parameterizing that where the state of the electron, say, or we are saying electron, but state of the qubit on this block sphere. So just in case you remember, so then this row, if you can, this is an outer product between this bra and ket. So it comes out to be this last line. This one is just a two cross. So it's essentially the density outer product of two vectors of two-dimensional vectors will become a 2 cross 2 matrix. Okay. So then this is the parameterization is this. It's 1 plus V dot sigma, where sigma is the Pauli matrices, the famous Pauli matrices. So this is how you can parameterize any qubit in general. Okay. So I'll go back to a little bit of quantum mechanics. So if you remember Schrodinger equation, so we are dealing with non-relativistic domain. So that means for us, Schrodinger equation is good enough. We don't have to go to the relativistic version. So whatever the solution gives. So because most of the time we'll be dealing with that. Although in some cases it might be odd. You might actually ask, why is this happening? Because as we'll see that many quantum computers are built on photons, and photons we know that are truly relativistic particles. They travel with the maximum speed and stuff. But the good thing is that even then, this non-relativistic description of quantum mechanics, that means using Schrodinger equation, it works. Okay, so for most of the practical purposes, this is sufficient as of now. Maybe in future we can know better when you get a truly relativistic version of quantum information theory and computers, but that's not today. So as I was saying, so these qubits are Ray's states. So they are called Ray in Hilbert space. So essentially, psi is the qubit. Okay, so psi can represent the qubit, and so normalization in this case, I'm just showing that normalization is our familiar normalization of psi. Now, there are two issues of quantum mechanics. That is, I mean, the left side, the right side is good because in quantum mechanics everything evolves by unitary operators. So that means it preserves the probability. So if you have a particle here at time t, and after some time it moves somewhere else, this entire description, I mean, transformation is described by unitary operator. Unitary operators will preserve this normalization. So you will get the particle and everything will make sense. Except that moment you measure something, okay, what we call the in normal lingo is that the wave function collapses. So the measurements are described by Hermitian operators and evolutions are unitary operators. For example, the Schrodinger operator, the Hamiltonian operator, the left side. So this is the this, when you evolve it further, this is just the time derivative. It is the Schrodinger equation is just showing the time derivative. So that means how it is changing instantaneously with time. So if you evolve it with this operator, if you solve this equation, you will get the evolution, and that will be described by an unitary operator. But the measurements, all the action. So you measure the spin of the electron, you measure the location of the electron, everything. You measure the momentum of the electron, or for any qubit quantum system, the wave function collapses, and so that measurement is described by Hermitian operator, and wave functions suddenly become localized. If you measure the position of the qubits, if it's an electron, then you will find that the wave function has collapsed at that place. And if you do multiple repetitive measurement, you will see that the electron is there all the time. Okay, so no confusion there. But so then it stops. It's as if it stops evolving with the unitary operator for short while after your measurement, and it collapses there. Okay, but collapse is a very problematic thing that we don't know how to handle properly, and we don't have complete control over it. It disagrees with uh, so for example, moment you ask that if the wave function collapses, does it collapse everywhere all around the universe at the same time? So if you find that, oh, an electron is here, does that mean the entire universe know at that instant that the electron is there? Or because it violates that the information takes time to propagate, right? So it's collapse is an instantaneous process. So that's why this problem mainly comes. But nevertheless, we can describe it using measurement operators, which are generally Hermitian operators. Okay, and of course, this famous quantum double slit experiment. So if you, this is again essentially motivated by Feynman. Feynman was the first one to popularize this description of quantum mechanics. He said, look, if you are throwing balls by two slits, so there are two holes and you are throwing balls, you will see that there are two lumps. Okay, and if you um, say passing a wave, for example, light is passing through two holes, then, and if you put a screen, beyond the screen light will interfere, okay, and create this slit pattern. So if it is a particle like small balls or bullets, whatever, then it is two lumps because that's a classical description. But if it is a wave, then you see interference pattern. The quantum mechanics showed that, okay, this description at the quantum world, this is not one-to-one. So something that is behaving just like a particle all the time can suddenly start behaving like a wave the moment you look at the other way. Okay, so for example, if you don't want to measure the which path or which slit the electron is passing through, then if you uh, have an electron beam gun, so that can fire electrons, and the electrons are passing through these two slits, you will see that they will create this interference pattern. So this experiment is actually have been done multiple times, and there are nice YouTube videos that actually shows that what happens. So if you are interested, you can just go and look it up. It's amazing. And there are many logical issues that come up with this. But the real interesting part is the moment you try to locate the electron, that suppose you ask, okay, the electron has started from the gun, so that means on the source, and it has hit the screen. So if I assume the electron is a particle, it must have gone through one slit, this or so the left one on the right one. So if you now keep something that can determine, that can say that, oh, the electron has passed through this left or right, moment you place such a device, it could be just a light, passing light, which gets deflected whenever the electron passes. Okay, if you keep it that way, even the minimal interference, so that means you can say that, oh, I will disturb the system very minorly, very lightly, so that nothing actually changes. I'll just try to read which path the electron is traveling. But no matter how you do, moment you try to measure, the interference disappears and you see two lumps. So that means it behaves like a particle. And more, and if you don't do that, you see an interference. And it is not just about electron. It is the photons behave same way. And I mean, so Einstein uh, got his Nobel Prize for this photoelectric effect, right? So that clearly showed that the light, what we take as the ideal thing about waves and thing, can behave in a particle manner, and what we call as photons, right? So the quantum of light is called photon. So light comes in packets and hits the outermost electron in this photoelectric materials, and they knock the electrons off, and that is the source of the current. So there is nothing specific about something like a particle or wave. It can be both. And this, of course, we know as the wave particle duality in our quantum mechanics first course. And this limitation to this limitation means how far you can test the nature of this has to do with the uncertainty principle. So Feynman beautifully explained this uncertainty principle in a line. I don't remember the exact line, but I can tell you the essence. So he said that the quantum mechanics is like a veil, okay? So the entire world is like a veiled world. So it just shows whatever you can see, only that. Beyond that, everything is like hidden. So whenever you are so if there are multiple possibilities, so you want to take something from point A to point B, it could be in time, it could be in space. So something is happening at point A and something is happening at point B. If there are multiple ways to achieve this, then there will be superposition of this. Superposition means it's wave-like, because we know that waves interferes. So that is the essence of superposition here in this case. So the moment you try to determine which path it has taken, the superposition disappears. So there will be no interference pattern. So the moment you want to uncover the veil, it will come up exactly as you are expecting. So if you want to try to look at, if you think the electron is a particle and you want to look at the electron, the path of the electron says, yes, I'm a particle. Moment you look in the other direction, that means you stop asking the question whether electron is a particle or not. Electron says, yes, I'm a wave, and both are valid. You cannot discard one for the other. And there is no, and this is the essence of uncertainty principle. Okay, so the Heisenberg uncertainty principle. So in his lecture, famous lectures, he demonstrates that you can derive the uncertainty principle from this argument, or you can say that this argument is a demonstration of that uncertainty principle. Okay, so in this lecture, I will not assume, I will not go anything, I mean, into more mathematics for quantum mechanics in this, because today's talk is not about quantum mechanics, but it is about quantum computation. So I'll try to keep it brief. Although I'll come back to a little bit of quantum mechanics slightly later, when because I need to talk about spins a little. Okay, but till that point, so we'll come back to our discussion of quantum computers. So let's try to understand just like we understand the classical computers. So classical computers, as you know, that is essentially performs logical operations, and these logical operations can be thought made up of these logic gates. Okay, so if you understand the operations of gate, you can perform any complicated task by combinations of them. For example, I have shown you uh, some standard gates that all of you know. So 2-bit gates. Okay, so A and B are the two inputs, and you have one output Q. Okay, if it is an AND gate, then this all of you know, so I don't have to explain this to you in detail. Just for completeness, if both bits are 1, you get 1. If it is if one of them or both of them are 0, then you get 0. So it's like a multiplication of these two binary variables. Similarly, OR is like it's at least one of them is 1, then it is 1, otherwise it's 0. And NAND is just negative of AND. so negative is like if the input is 1, then the negative is 0, and input is 0, then the output is 1. Okay, so this is the NOT gate, standard NOT gate. So NAND is essentially and NOT, and NOR is and or, and similarly you also know about the XOR gate, XOR gate. Okay, so I'm specifically talking about XOR gate because this is heavily used in there is a challenge associated with this in quantum mechanics, and it is used in quantum computers a lot. Okay, designing quantum computers a lot. So the XOR gate is 1, the output is 1 only when A and B are different. So if both of them are 0, it is 0. If both of them are 1, it is 0. Only if only A or B is 1. So A could be 0 and B could be 1, or A could be 1 and B could be 0. Then it is 1. So it's telling the exclusivity. Okay? So it's exclusively either one of them is 1 and the other is 0, then it outputs 1. So it says that two are different, the two inputs were different. Okay? But it doesn't say, of course, which one was 1. Okay? So this is the basic of classical computing. But we also know that we actually don't need all these gates separately. And some gates are more fundamental. I mean, as in that you can use these gates. For example, here I show you that whatever gates I was excuse me, sorry. Whatever gates I was talking about, you can mimic the action of all using just multiple NAND gates. You can also do this using the NOR gate. So these are the more fundamental or universal gates in that sense. Okay, so we can ask, is there a similar thing in quantum mechanics as well? So if we want to build quantum computers, so how would the gates look, or the logic gates look in quantum? So essentially what we are asking, so can we perform this basic building blocks of computing, the logical gates, the classical logical gates, can we mimic them using quantum computers? So can we build the logical gates with qubits? So I have not told you in physically what these qubits are yet, but I have given you the mathematics. I have shown you how to visualize them using block sphere, and I have given you some hints about the rules they obey. Now I'm asking a simple question. With those quantity, whatever it's called Hilbert space, they stay in Hilbert space. There are some up spin, down spin kind of thing. They stay in Hilbert space, and so they are qubits, and the actual electron could be a superposition, means all possible things are superposed on it. So that means it's simultaneously an up spin and simultaneously a down spin, or multiple projections, everything together. So these are called qubits. Now the thing is, with these qubits, can we build logical gates? If the answer is yes, then we can actually mimic the classical computation with computers, right? So we can ask the simplest. So this is the left, on the left side. This is the NOT gate, the most simple gate. It's a one bit gate, right? One input and one output. The input is 1, the output is 0. Input is 0, output is 1. It just reverses the input. So what would be the quantum version of NOT gate? So in qubit, we can say that a qubit in general is alpha part 0 and beta part 1. So we can express this in a spinor notation, two spinor notation, essentially a column matrix, alpha and beta. So alpha signifies the spin 0, I mean spin up part, say you can, projection of spin up part, and beta signifies the projection of spin down. So it's like what part is spin up and what part is spin down. Okay, but when you measure, you will measure mod alpha square. With mod alpha square probability, you will get spin 0 or the 0 state, and with mod beta square probability, we will get the 1 state. Okay, So spin up and spin down, or whatever you want to map. So that should be clear. Now, in this alpha beta notation, so what we are essentially saying that if alpha part is 0 and beta part is 1, then if we pass it through a quantum NOT gate, then it should output what? It should just flip the coefficients. So that means alpha part was 0 and beta part was 1. The output should be alpha part should be now of 1 and beta should be 0. So in the matrix notation, it will just flip the uh, coefficient. So alpha beta will become beta alpha. Not only that, now this is possible, and I will show you later that how in physical system you can realize this. So actually, you can, whenever you are doing this calculation using Sycamore, these are the logical steps you can easily perform. Q naught is possible. So Q naught is quantum NOT gate. Okay, so a quantum NOT gate will flip the coefficients of the qubit. So alpha beta will becomes beta alpha. So for example, so this is called a Pauli X gate. If you can see that if you using this gate, you can realize this Q naught gate operation. So if you apply this 0 1 1 0 matrix, this operator, which is a 2 cross 2 square matrix, on this column vector alpha beta, you will get beta alpha. So this is the operator that we are looking for. Okay, so that means the Pauli X gate, whatever, will work as a Q naught gate. So quantum NOT gate is essentially the Pauli X gate. So in the spinor notation, it will be represented by 0 1 1 0 matrix. Okay, so whenever we are realizing it in a physical system, we have to realize how, or think of how to implement this matrix in your system. So how to implement the logical, operations which can mimic this matrix. So then it can work as a Q naught gate. So in terms of qubit, what is happening is this. So it's, if you look at 0 and 1, so the Pauli X gate is doing a pi rotation, this 180-degree rotation of about the x-axis. So if you just hold around the x-axis, if you give a 180-degree rotation, 0 becomes 1 and 1 becomes 0, right? So that's what the NOT gate is doing. But if you look at the block sphere and think about the possibility, then you realize that, oh, in the classical system, there is just only one possibility, that flipping, right? But in quantum, you can have many more. For example, you can also rotate about the y-axis. You can also rotate about the z-axis. Okay, all these will give you different outputs. So rotate about y-axis will introduce some I, that means it's introducing some phase. The phase in itself may not be important, but we all know from our quantum mechanics course that the relative phase between two states can actually be important, and that's what creates all these superposition or interference creates all these interference patterns and not. So you could do this, which has no counterpart in classical. You cannot do this with classical bits. You can also do something known as Hadamard gate. So if you, Hadamard gate is interesting because if you just input 0, it gives you an equal mixture of 0 and 1. Okay, and if you give 0, then it gives you 1 plus 1. So equal amount of 0 and 1. And if you input 1, it gives you equal amount, but with a negative sign. So there is a relative phase. So if you want to understand the action of these matrices, then just mentally apply this matrix on this alpha beta column vector, and you will see what is the output. And from there, you can easily understand the action of this. For example, Pauli gate will make alpha beta to beta alpha, and Hadamard gate will give you alpha beta to alpha plus beta. 1 by square root of 2 is there because of normalization. Similarly, acting on beta, so the lower part, it will give you alpha minus beta. Okay, so this is what I was saying. Similarly, you can introduce something. You can also have something called a phase shift gate. So of which a particular phase shift by pi by 4 is known as a T gate. Okay, so but in principle you can have a arbitrary phase shift. So that means between 0 and 1, keeping the probability intact, you can introduce an exponential, purely imaginary part, so pure phase part, which does not affect the modulus, so it does not affect the probability, but you can introduce really um, not only just sign but a relative phase, and that's okay. That's okay for quantum mechanics. So that means it's not just possible. You can have many more possibilities of this logical operations. Okay, so it's actually far beyond the classical logical operation. But there is one drawback. Okay, the drawback is quantum mechanics is reversible. So that means whatever is moving forward in time, you can also say that it is moving backward in time. You cannot say the forward and backward. You cannot distinguish the forward and backward arrows in quantum mechanics. Okay, so that means all the gates that were irreversible. So, for example, the XOR gate. Okay, so XOR gate, whenever the A or B, one of them is one, it will be the output is one. But if I just tell you the output is one, you will not be able to say that whether A is zero or B is one, or A is one, B is zero, right? So it's irreversible. You cannot reverse it. However, with quantum mechanics, the catch is that since quantum mechanics is reversible, no matter how many qubits you put, it's going to be reversible. So that means you have to somehow bypass this problem. So it turns out that yes, it is possible. You can have something, you can mimic the irreversibility using more qubits. So with one qubit, it is not possible. So for example, you can think of two qubit gates. So now, so we have two qubits, one Q1, another Q2. So the total space now becomes 4-dimension. Both are up, both are down, or one is, the first one is up, second one is down, and first one is down, second one is up. I'm talking about the spins. Okay. So these four possibilities, and this in mathematics called it's an outer product. So this Q1, Q2 space is an outer product of these two spaces, and this coefficient alpha 1, alpha 2 are coming from this first qubits and second qubit. We can also smartly represent this alpha 1, alpha 2, alpha 1, beta 2, this thing as this a new column matrix of 4-dimension 4. This gamma 1 1 1 2 2 1 and 2 2. So the first one, so gamma 1 1 essentially is alpha 1 alpha 2. Gamma 1 2 is alpha 1 beta 2, and gamma 2 1 is beta 1. So 2 means, in the gamma notation, 2 means beta, 1 means alpha. Okay, and the first position, first index is for the first qubit, and the second position is for the second qubit. Okay, so this is the notation. So you cannot do XOR, but what you can do is called a C NOT gate. It is a control NOT gate. Okay, so there are two inputs and two outputs. If the first input is 0, the second one just passes. But if the first input is 1, the second one, you get the XOR output. So you see AB goes to A and A XOR B. Okay, so it just flips. So if you input this gamma 1 1, so if you input this blue column matrix and multiply this with this square matrix, this is the matrix representation of this control NOT. You will see that the gamma 1 1 and gamma 1 2 will just pass it through. Okay, but the gamma 2 2 and gamma 2 1 will flip. So gamma 1 2 1 becomes gamma 2 2, and gamma 2 2 becomes gamma 2 1. Okay, so the second two, so the first two, you see that first, so gamma 1 and gamma 2 2 means the first one is in the 0 state. Okay, so if the first one is 0, nothing happened. So the second one just passes through. But if the first one is 2, that means it is on the first the 1 state. So then the second index flips. So this is the quantum mechanical relation of this control NOT gate. Okay, the first qubit is then the control bit. Okay, and the diagram on the right is essentially giving you the equivalent gate picture. Similarly, you can have a swap gate which just flips the qubits. So if you start with a qubit and b qubit, value A and B, it just gives you the opposite. Okay, And this swap gate you can realize using the C naught gate using multiple times, and you can easily prove this by matrix identity. You know the C naught gate matrix when it is acting on the second one. You just have to figure out the C naught gate matrix when it is applying on the second, the first component. So that I have shown below. You can convince yourself that is the case. It's easy to understand. Okay, and if you just multiply these three matrix, you will get the swap gate matrix. You will see. So this shows that yes, using C naught gates in a clever manner, the control not gate clever manner, you can get this. And I've also drawn the truth table because we are interested in mimicking the classical computers. So C naught is the quantum equivalent of XOR, and swap is just the flipping around thing. So if you give both 0, C naught will keep it 0. But if you give 1 in the first register, that means A is 1, then the B flips. Okay, if B is 0, then it becomes 1. B is 1, it becomes 0, and so on. And you can see from the truth table. Similarly, you can also realize Toffoli get in quantum version, it just becomes CC naught. So there are now two control qubits which are connected with an AND operation. So I have given the table for this operation, but I'll not elaborate it further because if you know the logic gates, then all of you will immediately realize what I'm saying. It's just this is the quantum realization of this. Okay, so you have to just focus on the pink diagrams because that is how we are going to use realize this using quantum computers. So you can not, I mean, if you once you understand these, then you can build bigger operations. For example, this is an adder circuit. Adder, you know that it adds two binary numbers, and these are the inputs and outputs. So this is the circuit. Again, this with the information that I have given in here and here, using these two, you can actually work out in with on a piece of paper that this actually works out as an adder. So if you just A and B are 0, then the output is 0. If A and B, one of them is so it's doing the binary addition. Okay, and C in is the carry forward carrying index from the previous run, and C out is the carried over. So because whenever it I mean, there is a carry forward component, so then that will come out in the C out. So this part is standard as the classical thing. The interesting thing is that in this case, the relation is using Q gates, so the quantum gates. So these you can actually apply on a quantum computer. So there are quantum simulators available, that online simulators where you can easily build these gates and see how in a quantum computer this operation will do. This quantum simulators, some of them are free, and some of them requires a little bit of subscription. But anyway, so you can use any of them and just to try out for fun that yes, you can build this circuit and get an adder. But of course, you can do much better than that. Okay. The thing is, now in quantum mechanics, what you need to do is like you have to know how to build the unitary operations, okay? Because the evolutions are all described by unitary operators. So essentially, you need to figure out how to build any unitary operators, and that it turns out that there are multiple ways to do that, and you don't need all the gates. You just need, for example, this is a standard universal quantum gate set. Okay, C naught, Hadamard, the phase shift, and the T gate, which is essentially phase shift by pi by 4, 90 degree, 45 degree. So this set is sufficient. If you use this set multiple times, you can mimic any unitary operators. That means any possible quantum operation you can perform design with this 4 gates. So it's kind of fun if you want to play with circuits. Okay, so you can design your quantum circuits and you can see the outputs. Now, okay, so far so good. We are building quantum mechanical computers, and that can mimic the classical computing. But what is so special about this? Okay. remember, there are two special features of quantum mechanics that are actually coming, that are important. One is superposition, which we just discussed, right? That the qubit is a superposition of 0 and 1 state. But there is also another thing. It's called entanglement, quantum entanglement, which Einstein famously called the spooky action at a distance. It seems that mathematically it's like this. So whenever I was talking about this two-state system and all, so two qubit state, I told you that this is written as an outer product. Outer product is that cross inside the circle. Okay. So, but it turns out that not all two qubit states can be written as this. If you can write something as outer product, so that means qubit 1 and qubit 2 are independent. So you can assign anything in qubit 2 and you can assign another thing in qubit 1 independently. It doesn't affect one another. But it turns out there are states where you cannot do this. You cannot just assign one qubit 1 and randomly assign the other qubit as you want. No, because the moment you do something on qubit 1, something happens on the other qubit. And the real surprising part is that it doesn't matter where the other qubit is. Okay, it could be at the end of the universe for all matters. Okay, so some other part where you have no control inside a black hole, whatever. But that qubit will get an assignment according to you. But the most interesting part is that even though that happens, unfortunately you cannot use it to transfer information. So because this is an instantaneous transfer of information, which I said that a few minutes back, that this is a problem with quantum mechanics, understanding quantum mechanics. But even though this happens, you cannot use it to transfer information faster than the speed of light. But nevertheless, this phenomenon called entanglement is behind the source of quantum powers. Okay, so these two aspects, the superposition, the fact that you can have not only up and down, but all types of projection of up and down mixed inside a qubit. So one particular element is like representing everybody. Okay, so everybody means all the upspin, all possible projection of upspin and downspin at the same time. So whatever you are doing, you are working with all possibilities at the same time. Okay, so you don't have to run for the different possibilities separately. You just do one run of the computer and all possible computations are done simultaneously. So that is the power of superposition. And entanglement is saying that, look, you don't have to directly control the inputs or all inputs all the time, because if you have entangled pair, so you can control one, the other is automatically controlled. So it gives you immense control over how to manage computers. Okay, so now, so to understand this, okay, so below I show that how the spins. So this entanglement generally is understood in terms of spins, because this happens in an internal space, spin space. So and then below I show the Bell state, which is like the maximally entangled, the strongest possible bound you can say this entanglement you can have. Okay, the spin, I think I can kind of quickly pass through this part where I was going to talk about the quantum mechanics, but I think I'm running behind the schedule, so I'll just try to wind it up faster. See, in quantum mechanics, this spin is nothing that we have any classical intuition about. So spin is unlike anything we have seen. Okay, so for example, here I show this famous Stern-Gerlach experiment. It just shows that suppose you throw a spin half particle and filter out. So look at the first line. So from a oven, something is coming, the spin up or down, and you are filtering. So you are giving a magnetic field to project out the. It's like a passing through a double slit experiment. Okay, double slit, two slits. So you are stopping the negative Z component. So the spins are projected along Z direction. So upward Z is called spin plus and downward Z is called spin down. So you are stopping all the downward Z component and letting only the Z plus component pass. Okay, and then you can see the blue represent the spin Z component. You can do this in the so for example, you first create a particle in this and then pass the filter in the Z direction, select the Z plus part, and then apply a magnetic field in the X direction. Okay, so then the spins are also projected along the X plus and minus direction. So you can say that, oh, so that means I have started with an electron whose spin has plus half component in the Z direction, and both plus half and plus half minus half component in the X direction. So this color is not just blue, but it is an equal or a superposition of this yellow and red as well. But it turns out that you cannot do that, because uh, there is an uncertainty principle which stops you. Okay, so it says that the direction of spin you cannot ever fully recreate. So for example, uh, you cannot measure the X component and Y component and Z component of the spin simultaneously. It's simply not possible. For some reason, they satisfy. They're in quantum mechanical lingo. They are called non-commuting operators, incompatible operators. So they are not compatible with each other. So they are just like the position and momentum. So moment you measure the X component of spin, the Z component and the Y component gets erased. Okay, so you cannot assign X component and the Z component simultaneously. So we say that, I mean, moment we say spin, in our head that we feel like a ball is spinning around very fast, but that's not the correct picture, because if it's really like a ball, then you can actually measure the projection of angular momentum in Z direction, Y direction, X direction as you want, right? I mean, that's I mean, the angular momentum is a vector whose component is measurable, but not so in the quantum mechanical world. And not only that, there are even more interesting things. For example, if you have an electron and if you rotate the electron by say 360 degrees, so a complete turn, okay, its spin vector turns by half. So that means its spin, when it was, suppose it was pointing in some direction, and you take a full 360 degree rotation of the electron, now the spin vector will point in the opposite direction. And this is happening because it's spin half. So spin, that half factor is determining the spin is moving half as fast as, I mean, rotating half as fast as reality. And these things, we frankly speaking, we don't understand. Okay, we know how it works, but we don't know why it works or why this is so. It's not just electron and spin. You can do this. You can also understand this using polarization. So whenever you are going to watch a say 3D movie, you wear these polarized glasses just to filter out the left and right polarization. Or so this is essentially a quantum experiment you are doing. Okay, so these are filtering different projections. So this left and right projections you can treat is at qubit. Okay? So but even that projection you can understand the same rule there. Okay. Okay, so and I just wanted to say that even though it's an angular momentum, it's intrinsic angular momentum, and the quantum part of the quantum mechanics comes because the spin, it, if you measure the projection of the spin in any arbitrary direction, it can only take two values. It's like either spin up or spin down. This is unlike any classical vector that we see. Angular momentum of a ball can point in any direction, and it can have any component in the z direction or x direction or y direction, which is up to you to choose. Okay, it can have any value, but not so in case of spin. If you said that, say that, oh, this is my z direction, and I put a magnetic field to see that how many electrons are aligning with it, you will see that there are only two types of electron, either up or down. There is no middle. So something is like 30 degree, making 30 degree with the magnetic field, that's not allowed. Or say 42 degree with the magnetic field, or 132 degree with the magnetic field, those things are not allowed. Now we don't know. I mean, we only know that this is how it works, but we don't know how it works or why this works. Okay, And this entanglement is something even more interesting if you really understand want to understand the physics of this. So for example, here I show this example that Einstein quoted. So some particle, it's called pi naught. We don't care, okay, what is this about. So pi naught can decay to electron and positron pair. So this electron and positron is just the antiparticle of electron. So the rule is, because pi naught has no spin, this spin of the electron and the spin of the positron is always anti-correlated. So that means if one is up, the other is down. You don't have to know the spin of one without, I mean, if you know that, if you know just the spin of one, you can know the spin of other immediately, and you don't have to know anything else, okay? So let's say one side there is Alice, another side there is Bob. If Alice's electron has spin up, Bob's one must have spin down. We are calling both as electron, but one in reality one is electron and positron, and vice versa. Quantum mechanics does not predict the combination, but says that the measurements will be correlated, and you will get each combination half the time on average. Okay, so in quantum mechanics we cannot say deterministically these things, but if you measure. So this was the main theoretical, I mean, conceptual problem that Einstein really disliked. So if neither particle had either spin up or spin down until the act of measurement intervened, because see, the problem is happening is this, because we cannot assign a particular direction of spin before we measure. So that means just by measuring, we are assigning a direction. Now, if we measure only one, suppose Alice is measuring, but the other guy, Bob, is not measuring. But even by measuring on the Alice's side, the other spin is also kind of measured, right? So how is this possible that Alice and Bob could be completely separate in two galaxies differently? And even then it is happening simultaneously. So if neither particle had either spin up or spin down until the act of measurement intervened, Alice's measurement of the electron collapse wave function instantaneously produced the spin of the positron far away. So these three gentlemen wrote a seminal paper, which, by the way, is now topic of a hot debate and probably the next level research on quantum mechanics. So this question is far from settled. So what disturbed them? It turned out that there is indeed some disturbing factor. Okay, but this will be too much digressing, so I'll not elaborate on this further. So I'll come back. Okay. So coming back, so for practically, so we can say, okay, fine. So how to practical such Bell state, which is like the maximally entangled, so tied state, okay, tied with each other. So here I give you a prescription that how to create. So on the top, I just show you that, okay, this is the Hadamard gate we saw in few slides ago, and this is the circuit diagram that XY the X passing through an Hadamard gate, and then it's passing through a C naught gate, control naught, okay, the equivalent of XOR, okay. So and then the output will be Bell state, and this again you can, I have given you enough ammunition. If you want, you can work out this matrix and you can try out if you want, and you will see that you will get some state which cannot be written as, for example, look at this Bell state beta 00, okay. This is addition of, I mean, this is written, addition means superposition here. So it's equal projection of 0 0 and 1 1. So both 0 and both 1. So both up or both down equally superposed, and you cannot write them separately. It's not either 0 0 or 1 1. It's both equal projection uh, present there in the same qubit. Okay, so you cannot factor out one of them. You cannot say that I will set q1 as 0 but q2 as 1. That is not allowed. There is no 0 1 or 1 0 state. Okay, so these two are like tied up, and this is called the entanglement. This feature is called entanglement. So this is these two properties what makes the quantum computer special. Okay, so adding extra qubits so increases the probability space exponentially, because everything increases in powers of 2. So you are actually in so possibility space, how many kind of term it can, how many options it can simulate, or how many terms you can compute, increases exponentially. So adding a qubit is not just adding one extra component, it's enhancing the power exponentially, and that's why it's unlike the classical computers, and that's why building them is challenging. Okay, now so far I have told only about the good things, but there are some bad things as well. The real bad things is this. So I'll just since I'm running out of time. By the way, how much time can I take from now? uh, uh, 15
So we'll
20 minutes.
finish. Yeah, we'll finish
15 20 minutes fine.
Yeah, thanks.
Okay, thank you. So then fine. So the thing is, the main killer aspect is the noise. So so we might actually say that, okay, I take an electron, spin up and spin down, but I mean we are talking about as if this electron exists without any environment. Okay, but the thing is that you cannot isolate an electron and keep it in an environment where there is nothing to interfere. And by this environment, I don't mean the air or anything. Even the vacuum creates particle antiparticle pair all the time. So there is no clean environment for, I mean, it's almost impossible to get a clean environment for quantum systems. Okay. So so the coherence, this correlation between qubits, correlation between this fundamental blocks are lost. So this is the most major obstacle in designing quantum computer. Okay, so that is why. So Google's thing was tremendous step, because they could show that they have built a system which can calculate the probability space of 2 to the power 53, which is a huge number, and meaningfully. That means the error and everything that will be introduced because of environmental impact is manageable. The use of quantum states also leave the quantum computer much more vulnerable to errors than a classical computer will be, because you cannot clean the environment, right? I mean, you cannot clear it of the environment. So this is the drawback. So then something called a decoherence happens. Okay, decoherence could come from various directions, varying magnetic and electric fields. So you are doing it on Earth, so you cannot stop the Earth's magnetic field. So radiation from, if there is a slight warm object, so this one could be like, I mean, we may not even notice it. It's slightly above zero Kelvin or something. It can destroy you, spoil the entire calculation. Okay, or crosstalk between qubits. So these are tiny objects at nanoscale, even smaller, right? So if there is a slight fault in that, everything can, whatever your calculation you are doing could be meaningless. So and quantum noise, you cannot stop it from happening because it appears from the uncertainty principle. So that means it's a fundamental thing. It's I mean, you get quantum mechanics, you get quantum noise, and there is no two way about it. Okay? So quantum noise arises from the uncertainty principle and 0-point energy fluctuation. 0 point means in if you have solved the particle in a box problem in quantum mechanics, you know that the 0-point energy is not zero. If you look at a quantum simple harmonic oscillator, the lowest potential state is not zero. So it has a slight 0-point energy and around which it fluctuates. Right? It never stops. Okay, because if stopping means that it will have position exactly specified, and position exactly specified cannot be there, because then it will mean that the momentum is also determined. Momentum is zero and position is specified. That will violate the uncertainty principle. So uncertainty principle will force everything to move around all the time if you trap it somewhere. And not only that, there are more problems as well. So quantum error correction, which is a topic of intense research nowadays. Okay? So that is needed. But fortunately, there are algorithms and there are ways to deal with this, which are as of now moderately effective, but there are hopes that they will be very useful in the future. I mean, reasons to believe that is not just vague hope. Okay, so quantum error correction is essential for fault-tolerant quantum computation. So this is what uh, I said that near-term NISQ error, right? So this is like moderate level, so near term, so right now our qubits are noisy, but we can, if the number of qubits are low, we can manage the error to keep the error moderate, and so we can do meaningful computation, computation as Google showed. But it is really on the frontier, so there are probably handful of groups that can do it. But to do real good computation, we need much bigger qubits, bigger quantum computers, and the errors will be exponentiated. So controlling them will be nightmares. So right now we don't know any way to do that. And that's why we are, I mean, the day of full quantum computer or full quantum internet is in the future, not now. So it's impossible. Oh, and there are also some limitations of quantum mechanics. For example, no cloning theorem. So if you have a bit, so if you have a data in some hard disk, you copy it all the time, right? You have a USB stick, you copy the data. You, for example, I copied this presentation file from one computer to another. Okay, so it's like copying bits, and copying bits is very simple, but you cannot do this with qubits. It's not possible. There is a it's called the no cloning theorem. There are ways to get around it practically, but you cannot ever make a copy of an exact copy of a qubit ever. It's not possible. It's mathematically impossible. But of course, superposition, entanglement, measurement, and this, even the uncertainty principle, if you use it cleverly, can help you on to deal with this. So, so people are still working on, say, optimal length of a quantum circuit. So how big a quantum circuit should be to do meaningful calculation with controllable errors. Okay, but these are topics of current frontier research. Right now, most of these are moderately controlled, or but theoretically, most of them are very less understood. I mean, we are not there yet, as I can say. Okay, so so far I have been talking as if the circuit models, the logic gates, are not only type of quantum computers, but that's not the case. Okay, for example, there is something called adiabatic quantum computation. So it depends on the adiabatic theorem, which says the physical system remains in its instantaneous eigenstate. So for example, a state of a qubit will remain in that if a given perturbation is acting on it slowly. So essentially, it's saying if you disturb the qubits little, only slowly, and if the gap between 0 and 1 state, the energy gap between 0 and 1 state is large, then the Hamiltonian, actually the system will not change much. Okay, so that is the quantum equivalent of the adiabatic processes of classical thermodynamics that you all probably know. So then in this adiabatic quantum computer, what you do, you find a Hamiltonian operator. So essentially find a proper unitary operator for that, and then disturb this thing a little by a little, and you let the Hamiltonian evolve, the energy evolve, keeping the system in the ground state. And this is how you find the new ground state. So if you want to solve a particular problem, you start with a problem which is pretty close to that, and solve that problem, which is easy to solve, suppose, and then change that problem itself to this original problem, so that and this adiabatic theorem will guarantee that the solution will always remain the correct solution. So if you change the problem description itself little by little to your actual problem, the actual Hamiltonian, it will, you will, at the end of the evolution, you will get the correct answer. But you can also show that this adiabatic, whatever this computing technique can do, you can also achieve this using circuit-based model. So these two are essentially equivalent. Okay, so just to give you an idea, so there is already a adiabatic quantum computer available. This is a DOF quantum company, so they have a professional. It's called a quantum annealer. Okay, so this is also a very big chip, 128 qubits per conductive qubit. But there are some limitations, and these are not free, so they're very costly. But it exists. Okay, and not only this fantastic superconductor or an annealer, you can actually use a harmonic oscillator. For example, I take a demonstration from this Nielsen and Chuang, which is the standard book. of this quantum computer. I'll tell you about it in a few minutes. So you can actually use a harmonic oscillator if you know this problem. So then you recognize that this is the Hamiltonian operator, and you can write down the creation and annihilation operator like this. So and you can identify the states. For example, you can map the 0, 0, 0, 1 states like this. Okay, so you map 0, 0 to 0, the 0 of the 0th state of the ground state of the harmonic oscillator, and the second state with 0, 1 and 1, 0 with the superposition of 4 and 1 and 1 on 1, 4 minus 1. The key to understand, key point is this. So if you evolve, and if you evolve through a time pi by h bar by omega, which is a full cycle, what happens is all the even numbered state will will remain unchanged, wherever all the odd states will pick up a minus sign because of some phase transition. Okay, so all the even states will remain exactly as it is, but the odd number of states will pick up a minus sign. And if that happens, so if you do that, you notice that the under that case, the 1, 0 and 1, 1 will flip, whereas 0, 0 and 0, 1 will remain unchanged because they are mapped to even states. So 0, 0 and 0, 1 are not changing, but 1, 0 and 1, 1 are changing. So that means it's like if the first register is 1, then there is a flip in the second. Okay, so this you can realize through just a simple harmonic oscillator. Okay, this is, of course, right now there is no model. I mean, I don't know whether any company uses it, but in principle, you could do that. So it's essentially mimicking the C0 gate. Okay, so this is simple operation. So it's not just this. You can use optical photonic quantum computers, which is looking like the leading, apart from this the Sycamore kind of Cooper pair candidate. The optical photon quantum computer seems to be the topmost candidate for a viable quantum computer. So because photons are, I mean, they are easy to get, cheap. You get photons all the time. And nowadays, even a single photon detector and a single photon creator are available, so that they are not problem. And they are high, I mean, they don't interact with each other. So that means if you store a quantum state, for a very long time, they'll retain that state. The interference is very low, and they can easily interact with matter and thing. And if you can control that matter interaction with photon, so then you can use them as a quantum computer easily. So these are the so uh, quantum computing model. Just for 1 second, I wanted to know how much time do I have, because I was planning to cover some algorithms, but these are not necessary. If I don't have time, then I'll just skip through it. Okay.
Sir, we finish 12:30.
Okay, so in that case, uh, so I actually describe the two most well-known algorithms, quantum algorithms. One is Shor's algorithm, so which can factorize the big prime number. Why this is important? Because in all our security protocol, this prime factorization is the key. So if you can factorize big prime numbers fast, then you can break all this encryption that are currently available, right? So this is the challenge of quantum thing. With quantum computers, Peter showed that you can easily find, I mean, if you have a good, large, fault-tolerant quantum computer, you can easily find very big uh, numbers, the prime factors of very big numbers easily. Okay, and that is the danger or potential of quantum computers, and that's why it's so important to think of quantum computers in security and other related fields. Similarly, so this is another algorithm. This is Love Kumar Grover. He was I mean, he is an Indian, but settled in US. So he showed that using quantum computers, you can easily find uh, a particular object from a very big set. Okay, so you can pick. So essentially, he formulated a problem like this. So if you have a function well, which is 1 for one particular value, but for every other set it is 0, you can find for which particular value it is 1 easily. So it's essentially finding uh, it's a search algorithm. Okay, and this algorithm shows that I mean, it is very simple to understand, and you can understand this geometrically. But anyway, so I can skip this because it's uh, and so in 2017, somebody actually implemented this 3-qubit Grover search. Now, 3-qubit Grover search is not fantastic in terms of use because it's only 3. You are finding one number out of 3, but it shows that this works, and that is what is important, because we are not talking about now, we are talking about in future. If this is possible, then many things are possible in near future. If you quantum computer can break the security protocol of today's, then you might have to come up with better security protocols very fast, because you never know, because it could be like next year or this year or 10 years down the line, there are good enough quantum computers, and once you have them, you are in business. Okay, so I have come to the end. So essentially, I hope I have given you the state of the art of how we understand quantum computers, and how um, using simple logic we can understand their operations. Okay, so what are the scopes? So as you have understood, or I just told you, that in cryptography there is a huge scope, because if the quantum computers can break today's security protocols, then you need to go back to the board and start from one. Similarly, the search problem, searching, if the Grover search algorithm is one such example, but there are now many. Okay, and Grovers and Shors are famous because they were like the first algorithms there, but now there are a lot of quantum algorithm is a very active domain. Similarly, it can do optimization problems, you can do quantum simulations, you can solve chemistry problems. Google already demonstrated that. You can actually try to figure out double slit experiment paths, actually, and people are trying to do that. So these will take, I mean, like take us to Feynman's dream, probably, that understanding nature with nature. It will tell us that what is the issue there, why can't we do that. Okay. On more practical side, it can do drug design and more abstract, but maybe in future more impactful. For example, whatever is happening in the Large Hadron Colliders, where this particle collider at CERN, there you have truly an unimaginable level energy, and you are manipulating quantum objects. Okay, so there you need some quantum simulator to reproduce results accurately, and so quantum computer, if we have that, we can do wonderful there. And last but not the least, machine learning is all around us. Like every direction you look at, it's like machine learning or artificial intelligence and so on. But it's not just classical computers. With quantum computers, the probability of machine learning, it increases. I mean, the capacity of machine learning increases exponentially. Okay, so you can sample a probability space that is much bigger than what you can sample classically. Okay, so the scope is huge. So I'll just show you the snapshots of 3 papers. So for example, this is the optimization problem is already used in for some Higgs problem. So the problem is not right now important, but it shows that deep problems that there is no other way to solve it, you can use it, and maybe in very soon, whenever that era comes, we can do it. So this is one paper that one of our, so Utkarsh Azad is one of our students, and Professor Harjinder Singh is my colleague. So he essentially started the quantum center here, of which I'm a part. So they have solved some hydrogen, so helium um, and plus hydrogen atom interaction, and simulated with quantum computer, and showed that it agrees exactly with the theoretical prediction. Okay, so this is like, it's evidence that yes, quantum mechanical computers are there, and they can solve meaningful problems from domains. So this is a very recent paper. Very recent means impact wise very recent, but there are more modern techniques even after this. But it shows that even in very heavy data intensive things at like a hadron collider, where there are things with high energy. So where April will not assume that quantum computer will work, because even though it is quantum, things are happening at a relativistic scale. Okay, so this is, particles are colliding very fast. So this is happening in relativistic scale, and everything we described is depends on non-relativistic domain. But even there, you can do wonderful things and with quantum computers. Okay, so so these are not just claim; there are some demonstrations as well, and a lot of this you can actually do it yourself because using the quantum simulators that are available. So with this, I think I'll stop here. I think I have already overshoot my time. Thank you.
So thank you, sir. Thank you so much. So participant, if you have any questions, please raise. I will unmute and you can ask. Ganapati Ram, sir. Yeah.
For your nice presentation, sir.
Thank you.
Sir, okay, sir. Sir, I have here two doubts, sir. So, which particle is responsible for performing calculations, either as electron or photon, sir?
Oh, okay, so in photonic quantum computers, it will be photon. But right now, so for example, in Google's quantum computers, it's not just one electron, but electron pair. So Cooper pair. So in superconductors, there are pairs of electrons. So they are those. So the answer is not clear which one will win, but you can use both.
Okay, sir. So if it is an electron, so it is a fermion. So the spin off is there. If it is a photon, so there is an boson. So it is an
Very good question.
plus.
Photon has no spin up, spin down, right? But
Yes, sir.
photon has polarization. Photon has left polarized or right polarized.
Okay.
So you can use that as just like you can use a spin up and spin down. But this is a very
Yes,
good question. Yes.
okay, sir. Sir, one more doubt, sir. So,
Yes.
if you're given in the build state, so 0 0 minus 1 1, so it is in build state. Why it is not a reverse? 1 1 minus 0 0 is not in the build state. The same way, 0 1 minus 1 0, so it is in build state. So why it is not 1 0 minus 0 1 is not in the build state?
No. So can you repeat the question a little slowly, because I didn't catch
Sir,
everything.
0 0 minus 1 1, so get 0 0 get 1 1, so it is in the build state, you go say, and so but why
Oh,
it is
no,
a
no, no.
reverse is not in the
Wait. See, so you look at this table. Can you see the screen? Look at this
yes,
table.
sir.
All of them are build
Yes.
state. Okay, so 0 0
Yes,
0
sir.
1 1 0 1 1. So the output. Look at the output. 0 0 plus 1 1. 0 1 plus 1 0 0. So it's out of the four possibilities. If you eliminate two and add the other two, then it becomes a build state. Add means plus or minus doesn't matter. It's fine.
Oh, okay, sir. Okay, thanks.
Yeah. Any other question?
Raja sir, can I ask a question, sir?
Sir, good afternoon, sir. Thank
Yes.
you for your nice presentation, sir.
Thank you.
Sir, actually, nowadays, what are the main challenges in implementing quantum algorithms on current
Yes.
quantum hardware for real-time applications?
Correct.
Like cryptography or optimization or machine learning?
Yes.
Whether it is possible?
Yeah, the main challenge is to scale it up. You have to get a handle on the noise, right? The error thing. So first of all, the technology to build, a quantum computer with large qubits, many qubits, is challenging, because you understand these are quantum level things. So if you have to manipulate one photon or one electron, it's difficult. Now you're talking about 54 such electron pairs or 54 such photon pairs, the photons, and manipulate them precisely. It's difficult, possible, but now on top of that, you are losing some because of the errors. So this is the bottleneck.
Okay. Sir, it is whether it needs a special hardware device for implementing such contents.
Yeah, I told you So it could be like, essentially it boils to this. So with what you should build a qubit. Okay. So you will build a qubit with superconducting Cooper pairs. You can build qubits with photons, single photons. You can build qubits with, say, laser pulses. You can build qubits with nuclear magnetic resonance, so nuclear spin states. Okay. So all these are possible in principle, but which one is scalable is a different question. It looks like the photonic quantum computer will win, at least as of now.
Okay. Okay, thank you, sir.
If you have any other question.
Hello.
Yeah, hello. Good afternoon.
Sir, can you send me this PPT on a WhatsApp group?
So I can send it to Dr. Maheshwari, and probably she can. I don't know of the WhatsApp group. I can definitely send the slides. No problem. I'll do that.
Okay, ma'am. We will share it in the group. No issues. Dhanush sir, if you have any questions,
Hello.
Sir, am I audible, sir?
Yes, yes.
Sir, actually, myself, Dr. Dhanush from Rathinam Arts College, sir.
Hello.
Sir, I have a doubt regarding the quantum yields.
Quantum what?
Dr. Sudeep, sir. Actually,
Yes,
I'm
yes.
working on
Quantum
a
what?
nanomaterials called as quantum dots.
Quantum dots, yes.
sir. Quantum
Yes.
carbon dots. Yeah, we are at particular stage. We used to calculate the quantum yields. So what parameter we are using is that we use the absorption and emission values to determine the quantum yield.
Yes.
Yeah, is there any other alternate methods to calculate the quantum yield other than the using absorption and emission values, sir?
At least I don't know of any other better method.
Okay.
So I have not seen anyone dealing this question with a quantum computing approach. At least I have not seen.
Okay. Okay, sir.
Yeah.
Thank you, sir.
ma'am. Thank you, sir. Ma'am.
Yeah. Hello.
Good afternoon, sir.
Good afternoon.
I have a question.
Your voice is cutting actually.
Am I audible?
Yes, you are audible.
Can be implemented or blocked?
No, I am sorry, I can't hear you. If someone can tell me what this question, what our question is.
Okay, sir. She share it in a chat. I think it's a network issue for. Okay. So Dhanush sir, give you the vote of thanks.
Yes, sir. So myself, Dr. Dhanush from Rathinam College of Arts and Science, and I take immense pleasure in delivering the vote of thanks on this good occasion. So primarily, I thank our CEO, our principal, our vice principal, and dean R&D for their invaluable support and approval to conduct this online FDP. Next, I thank the head of computer science, Dr. Raja and Dr. D. Velumani, sir, and our head Department of Physics, Ms. D. Uma Maheshwari ma'am, for taking the pain in conducting this 7 days on FDP. I thank all the HODs of physics and computer science also. And the primary thing, I thank wholeheartedly Dr. Sudeep Mitra sir for his knowledge sharing, his valuable time, and his clear-cut explanation and smooth explanation on quantum computing. And I thank very much for your patient response for the audience queries also, sir. A wholehearted thanks for your time and your knowledge sharing, sir. So finally, I thank the department faculty members, participants, and other people who worked hard for successful completion of this first day online FDP. Thank you all once again. Thank you, sir. Have a great day.
Thank you. Thank you. I should thank you for giving me this opportunity. It was very nice of you to invite me, and it was my pleasure to talk with you. So if you have any question, you can send it to me by email. I'll try to answer as much as I can, and I'll share my slides. So thank you very much.
Please stay connected. Thank you, sir. Thank you very much.
Thank you, sir. Thank you so much for your presentation.
It's my pleasure.